friends, myself Dr. R.P.S. Chauhan, welcome you all in my next lecture of subject microprocessor and microcontroller. In this lecture I am going to discuss the counter and the delay programming, how the counter and the delay programming can be considered or which can be generated in this program with the help of the logic or assembly language program. So, the counter is nothing but a counter is designed simply by an appropriate number into the register by loading the appropriate number into the register. So, counter is nothing but it can be used to count an event which can be occurs, or we can say that we can use the up counter and down counter as per our requirement. So, counter is nothing but it can be designed simply by loading an appropriate number into the register which can be incremented or decremented using this INR or DCR instruction. So, with the help of this INR and the DCR instruction, we can perform this counter operation. So, a loop is used to update the count value. So, here to implement the counter, we need to initialize the counter first. The value of counter is loaded with the particular value, whether it is the up counter and down counter, and here display this count value and update the counter by incrementing or decrementing. If we want to design up counter, we use INR instruction. If we want to design a down counter, we use DCR instruction and check the final count. So, if this final count is reached, if it not reached, then the loop is iterated again and loop is continue. If the count value is not reached, then the loop is continue, and if it is count value is reached, then it will terminate the loop and it will comes from the loop. So, this is the flow chart of the counter. So, in this flow chart we need to initialize the count value. This is the first step which is required, and then display this count value means this is the final value or this is the initial value. So, if we design to design a down counter, so we initialize the count value with the last value and then keep on decrementing it and check the value whether it is reaches to the last value or not. So, this is the loop and this is the structure of the counter. Next is the time delay. To design a time delay, a register or register pair are used to load the value depending upon the time delay is required. So, how much time delay is required will depends upon the value which can be loaded into the register. The register or register pair are decremented until it reaches to the 0 value. So, we can use register or register pair, and this register value can be decremented and check whether this value reaches to the final value, that is 0 value or not, with the help of the conditional jump instruction. So, remember that here conditional jump instruction is used to check the value, final value. The loop generate the delay depending upon the clock period. So, here the loop will generate the delay and it will depends upon the clock period of the system. The flow chart of the time delay is given. So, here the body of the loop, and if there is a condition, this condition is satisfied. If this condition is not satisfied, then the loop is continue, and if the condition is not satisfied or condition is false, so then it will comes out from the loop. So, this is the structure of the time delays. Next is how to calculate the time delay. To calculate the time delay, identify how many T states and instruction required by keeping in mind that a T state is nothing but it is a 1 clock cycle. So, it is required to keep in mind the T state nothing but it is a 1 clock cycle. We can calculate the time delay with the help of this formula. Time delay is equals to number of T state, it is multiplied by the clock period. So, what is this clock period? It is nothing but the T state is nothing but it is a 1 clock cycle. So, it can be the clock period can be calculated with the help of the clock input frequency. If the clock input frequency of the microprocessor is 3 megahertz, so this frequency is need to divide it. So, the time period is nothing but 1 over the clock input frequency, and accordingly we can get the time period. So, here for example, the instruction move a comma b. So, whenever microprocessor execute this instruction, it requires 4 T state during the operation. Therefore, if the clock frequency of microprocessor is 3 megahertz, so the time period comes out that is nothing but 0.33 microsecond. The time delay generated by the instruction, that is move a comma b, is the time delay is equals to the number of t state required by this instruction. Since this instruction will require 4 t state, so this is multiplied by the time period, that is 0.33 microsecond. So the total time delay generated by this move a comma b instruction is 1.32 microsecond. So this is the technique through which we can calculate the time delay by multiplying the number of t state required by the instruction, that is move a comma b by the time period, that is nothing but the 0.33 microsecond. Now, following techniques which are used to design a time delay. So, these are the technique which are commonly used to design a time delay, that is using one resistor, using resistor pair and the nested loop. So, these are the three techniques which are commonly used by using one resistor, by using resistor pair or using nested loop we can calculate the time delay. So, let us see how time delay can be calculated with the help of one resistor. In this method, a count value is loaded into resistor and use a loop to produce certain amount of time delay. So, in this case we load the count value into the resistor and use a loop to produce a certain amount of time delay. The first instruction, so this is the example of the program which is used to generate the time delay. So, here the one resistor, that is resistor C, is used. So, here the resistor C is loaded with a value, that is FFH. So, first instruction, that is initialize the loop of the counter. So, this instruction is used to initialize the loop counter. So, here the resistor C is used as a counter which is initialized with the value FFH, is executed once and it requires 70 states. So, remember that the resistor which is used to hold the count value is executed one and it requires 70 state during the time delay generation by the one resistor pair. The following two instruction from a instruction form a loop that requires 14 t states. So, following two instructions are DCRC and JNZ loop instruction. So, this instruction will require 14 t states. So, 10 plus 4 is 14 t states. So, these instruction will require the 14 t state and it execute and repeat 25 times until C becomes 0. So, it will repeat 25 times until this value of C becomes 0. Generation of time delay using this C resistor. So, this is the example, resistor C is used to generate a time delay, resistor C is used to hold the count value and this count value is decremented with the help of instruction DCRC. Now, with the help of instruction, that is the conditional jump instruction, will check the value of C whether that is 0 or not, and the total t state required by these instruction DCRC and JNZ is nothing but 14 t state. Now, to calculate the time delay in this last iteration of the loop, JNZ instruction, when the condition is true it takes 10 t state and when the condition is false it takes 70 state. So, this is required to remember, when the condition is true JNZ instruction will take the 10 t state and when the condition is false it will take 70 states. Therefore, we deduct 3 t states from the total delay to get the accurate delay. That is why we deduct 3 t state from the total delay to get the accurate delay. So, here with the help of this equation, that is t delay is equals to delay outside the loop plus delay of the loop, that is T L, we can calculate the total delay. So, t delay is nothing but the total delay, T O is nothing but delay outside the loop and T L is nothing but delay of the loop. So, with the help of these value we can calculate the total delay generated by one resistor pair. So, T 0 is nothing but sum of all delay outside the loop and T L is calculated as T L is equals to the time period which is multiplied by the loop t state, that is T L, and it is multiplied with number of the iteration, that is 255, in case the maximum value which can be loaded into the one resistor is 255. So, this way we can calculate the total delay generated by one resistor. Next is time delay generated by the resistor pair. To increase the time delay, if you want to increase the time delay further, we use resistor pair instead of resistor. So, here the resistor pairs are used to increase the time delay to hold the maximum count value, that is FFH. So, with the help of resistor pair RP, we can load the maximum count value, that is FFH. Minor problem arises that during this method, that in this case, since we are using the resistor pair, so accordingly we use instruction DCX RP and INX RP. But remember that during the execution of INX RP and DCX RP instruction, this instruction will not modify the status of the flag. So, this is the major problem by using this time delay by using resistor pair. To overcome this problem, we logically OR the content of two resistor which is used to generate the time delay. So, here we perform the logical OR operation to overcome this problem. So, here the we logically OR the content of 2 register in the register pair and then checking the 0 flag. So, again we check the 0 flag, that is nothing but the conditional jump instruction, and accordingly we can perform the required operation to generate the time delay with the help of register pair. So, here this is the program which is used register pair, that is register pair BC register pair is used, which is loaded with the value that is 1000 H. The T state required to execute this instruction is 10 T state, and then the DCX B instruction, it will execute. When this instruction is executed, the BC register pair is decremented by 1, and the T state required to execute this instruction is 6 T state, move A comma C required 4 T state, ORA B instruction required 4 T state, and JNZ loop instruction required 10 T state. When the condition is true, it requires 10 state, when the condition is false, it required 70 state. So, time delay generated by register pair using the formula T delay is equals to TO, that is the delay outside the loop, and the delay, calculate the time delay, loop delay. So, that is TL is nothing but the loop delay and TO nothing but the delay outside the loop. So, TO is nothing but 10 T state, this is the delay which is outside the loop, that is 10 T state for the LXI instruction, and TL is nothing but 24, 24 is nothing but the T state for the 4 instruction, and the loop is repeated 4096 times, because the count value which is loaded as 1000 H is the hexadecimal number, the equivalent decimal number is 4096. So, the count value can be repeated that 4096 times, and here we reduce 3 T state when the condition is false. So, this 3 T state can be deducted to get the accurate time delay. So, finally, the time delay which can be obtained as T delay is equals to 10 plus 98301. This 98301 is nothing but the value of TL, and it is added with the 10 T state, which is nothing but the value of T0, and it is multiplied by 0.33 microsecond. This is the time period of the 8085 microprocessor when the clock input frequency is 3 megahertz. So, time period comes out to be 0.33 microsecond. So, when we multiply this, we get the delay that is 32.77 millisecond with the help of register pair. So, with the help of register pair, we can able to generate a delay that is 32.77 millisecond when the clock input frequency is 3 megahertz. The time period is 0.33 microsecond. Next is the time delay generated by the nested loop. What is the nested loop? Nested loop can be set up by using 2 resistor for the 2 loop counters and updating the right resistor in the right loop. Flow chart of the nested loop is as follows. So, nested loop is nothing but one loop inside the another loop. So, here this is the flow chart. Initialize the loop 2, body of this loop 2, then initialize the loop 1, then body of loop 1, update the count 1. Is this final count? If no, then repeat this loop. If the final count is this, comes out from the loop, update the counter 2, and again check is this the final count. If not, then repeat the loop and comes out from the loop if the condition is true. So, this is the example, this is the flow chart of the nested loop. So, the nested loop is also used to increase the time delay, total time delay in a program. So, here the program which is the example of the nested loop. So, here the 2 counters are used, that is MVI B and MVI C. So, here B and C 2 counters are used. So, MVI B, the count value is 10H, and this instruction will require 70 state. Then the second counter MVI C FFH, again the T state required, it is 70 state. DCRC instruction required 40 state, JNZ loop 1 instruction required 10 T state. When the condition is true, it requires 10 T state. When the condition is false, it requires 70 state. DCRB instruction required 40 state. Again JNZ loop 2, this instruction will require 10 T state when the condition is true. When the condition is false, it requires 70 state. Now, to generate the delay with the help of nested loop, the delay of inner loop which is given by TO1, that is 70 state, and this is the T state for this instruction MVI C FFH instruction. So, this instruction will require 70 state, and TL1 is calculated, the 255 multiplied by 14 minus 3, that is 3567 T state. So, what is this 14 T state for the DCRC and JNZ instruction? The JNZ instruction, when the condition is 10, condition is 2, the T state is 10, and for DCRC instruction, that is 4, 10 plus 4 is 14 T states, and it is repeated 255 times for this value FF. So, 255 decimal minus 3 for the final JNZ when the condition is false. So, T loop 1, that is 7 plus 3567. So, the value comes out, that is 3574 T state. Now, delay of outer loop, that is TO2, which can be calculated 70 state for this MVIB10H instruction. Then TL2 is 16 multiplied by 14 plus 3574 minus 3, which comes out to be 57405 T state. So, 14 T states for the DCR and JNZ instruction and 3574 T state for the loop 1, which comes out the value from this loop 1. Repeated 16 times for loop 1, repeated 16 times for this value 10, which is 16 decimal minus 3 for the final JNZ instruction. Therefore, the total delay which comes out to be 57412, it is multiplied by 0.33 microsecond, which is the time period of the 8085 microprocessor when the clock input frequency is 3 megahertz. So, the total delay which comes to be 18.945 millisecond. So, with the help of this nested loop, we can able to generate the time delay of about 18.945 millisecond when the value can be loaded into the register, that is B register, that is 10H, and C register, that is FFH. So, this is the example of the time delay which can be generated with the help of the single register. So, see, this is the example of the time delay. So, here the first example is nothing but with the help of the register, that is C register. So, here the C register is used to hold the count value, and with the help of this count value we can able to generate the required amount of time delay by keep on decrementing the value of C, and if this value becomes 0, then only the processor will come out from the loop. It will come out from the loop, and the required amount of delay can be generated. So, this is the formula which can be used to calculate the delay with the help of one resistor. So, this is the total delay which can be generated, that is T delay is delay outside the loop, T 0 plus delay of the loop T L. Next, the resistor pair which can be used to generate the delay to increase the amount of delay. The nested loop is used to further increase the value of the time delay generated by the microprocessor or with the help of the program. So, this nested loop is nothing but the loop comes under the another loop. So, here the loops can be nested. So, this is the example of the nested loop. Now, let us see the program which will perform the down count operation and generate the delay simultaneously. So, the program statement is write a program to count continuously in hexadecimal from FFH to 00H in a system with a 0.5 millisecond clock period. Use register C to set up a 1 millisecond delay between each count and display the number at one of the output port. So, here three things is required to done. That is the first thing that to design a down counter, hexadecimal down counter, which will count from FFH to 00H, and system will generate a delay of about 0.5 millisecond between each count and the display the number, that is the count value at one of the output port. So, this problem has the two parts. The first is to set up the continuous down counter, and the second is to design a given delay between two counts. The hexadecimal counter is set up by loading a register. So, here we need to set the hexadecimal counter by loading the register with an appropriate starting number and decrement it until it becomes 0. So, here this is the example of counter, the count value which is the maximum value which can be loaded into the counter, and this value is keep on decrementing till it reaches the final value. So, after 0 count, the register is loaded with a value FFH, because decreasing 0 decrementing it 0 will result, means if we decrement the value, that is FFH by 1. So, the result is 0. So, this is nothing but that is -1, which is again FF in the 2's complement. The 1 millisecond delay between each count is set by using the delay technique. So, this is the requirement in the program. So, delay loop including two instruction, that is DCRC and JNZ instruction having the 14 T states. So, see here the delay loop will consist DCRC instruction and JNZ instruction. The total T state, that is 4 plus 10, that is 14 T states. So, here the 14 T states is there, and the B register is used to initialize the value, that is 00. When this value is decremented by 1. So, the value becomes FF. So, here we need to initialize B register with 00H, and if we decrement this value by 1. So, the value of this B register, that B is equals to FFH, because here it is required, because we need to design a down counter. It will count the first value, that is FFH, and it will keep on decrementing up to this 00. So, here therefore, the time delay TL in this loop without accounting for the fact that JNZ requires 7 t state in the last cycle, because count value will remain same if the calculation take into account the difference of the t state. The meaning is that in the previous case, when we generate the time delay with the help of the single resistor pair or nested loop, we deduct -3 to get the accurate value of the time delay. But in this case, during the designing of this down counter, if we decrement the value, the value of count will remain same, because here the if we decrement the 00 by 1. So, the again it will the count value becomes the FF. So, here we not deduct 3 from this to calculate the accurate delay. So, here to calculate the delay, we use this formula TL is equals to 14 t state, and it is multiplied by the clock period, and here we need to obtain the count value, because the count value is not given. So, we need to find the count value with the help of this equation. There is this TL is equals to 14 t state, it is multiplied by the clock period, which is given 0.5 microsecond. Here 0.5 millisecond clock period is given in this program. So, here the clock period is given, that is 0.5 millisecond. We need to find the count value. So, we use this instruction, that is 14 t state is multiplied by 0.5 into 10 to the power minus 6, that is for microsecond, and we need to calculate the count value. So, this is the program which is used to design the down counter, and it will generate a delay of 0.5 millisecond if we if the count value is loaded into the count register, that is C register. The delay outside the loop include the following instructions. So, this is the instruction which is used, the delay outside the loop, that is DCRB instruction. It requires 4 t state, MVIC count, we need to find the count value. So, it requires 7 t state, move A comma B, it required 4 t state. Then output, we need to display the value into one of this ports. So, here we use instruction output. So, it requires 10 t state, and the conditional jump instruction, that is JMP instruction, unconditional jump instruction. So, JMP instruction. So, here that is 10 t state is required. So, total t state which is obtained in this particular program is 35 t state. So, here the total t state, that is 35 t states. So, delay outside the loop, that is t 0 is equal to 35 t state, it is multiplied by the time period which is given, that is 0.5 microseconds. So, accordingly we get 17.5 microsecond delay. So, with the help of this we can get the delay of, that is 17.5 microsecond. So, total delay, time delay, which is calculated with the help of this equation, TD is equals to T 0 plus TL. So, here TD is nothing but the total delay, T 0 is nothing but the delay of or the time outside the loop, delay outside the loop, and the TL is nothing but the loop delay. So, here the total delay which is required, that is 1 millisecond which is required. This is the total amount of delay which is given in this program. Then 17.5 the delay outside the loop, that is the value of T 0. So, the value of T 0 is given, that is 17.5, that is microsecond, and TL is nothing but 7 into 10 to the power of minus 6 into the count value. So, with the help of this we can obtain the count value. The count value comes out to be 8CH. So, the equivalent is 140. So, this is the equivalent of the value, that is 8CH. The value 8CH is loaded into the register C to generate a delay of about, that is 0.5 millisecond. The delay about 1 millisecond, that is in the program. So, here the clock input frequency is given, that is nothing but the according to this clock input frequency, the time period is given, the clock period is given, that is 0.5 millisecond, and with the help of that we can able to calculate the 1 millisecond delay by obtaining the value of count. So, here the count value which comes out to be, that is 8ch. So, here with the help of this program we can able to design a down counter which will count the number from FF to 00h. So, the initial value, that is FF, which is a down counter, it is will count from FFH to 00h, and between each count it will generate a delay of 1 millisecond. So, here the 1 millisecond can be generated by obtaining the value of C register, that is 8ch. So, this is the example of the program which can be able to program to generate a delay, that is 1 millisecond, and it will count the value, that is FFH to 00h, when the system with 0.5 millisecond clock period is there. So, this is the example of the time delay generation. So, here in this session we have discussed the how to design a counter and how to design a delay. So, this counter just I am repeating these things to design the counter. How we design a counter? With the help of the counter is designed simply by loading an appropriate value, and the counter is can be designed with the help of the increment and decrement instruction. If we want to design a counter, the up counter, we use this INR instruction, and if you want to design a down counter, we use DCR instruction. So, this is the flow chart which is used to design a counter, initialize the counter, display and update the count value, check the value whether it is reaches to count value. If it is not, repeat the loop, and if this reaches the final value, comes out from the loop. Now, the next example is nothing but, the next slide is nothing but the generation of time delay. The time delay is nothing but with the help of program we can able to generate the time delay between the two events. So, this time delay can be generated with the method which is commonly used, that is by using one resistor or resistor pair or nested loop. So, this is the general flow chart of generating the time delay. So, this is nothing but the body of loop. So, during the generation of time delay, we will initialize the resistor with a count value, and will keep on decrementing this count value and check whether the counter reaches the final value or not. If it is not reaches the final value, then repeat the loop, and if it reaches the count value, then come out from the loop. So, this is the flow chart of the time delay, and this is the example of the generation of time delay with the help of the resistor pair, resistors and nested loop. So, here the time delay can be generated with the help of the single resistor. So, this is the program. With the help of this program, we can able to generate the time delay with the help of C resistor. So, here single resistor is used. With the help of this resistor, we can able to generate the time delay. So, whenever microprocessor execute this instruction, so accordingly here the T state is very important. We required to remember that how much T state is required to used by the microprocessor to execute the particular instruction. So, this MVIC instruction uses 7 T state, DCRC instruction uses 4 T state, and JNZ instruction uses 10 T state. So, when the condition is true, it requires 10 state, when the condition is false, it requires the 7 T state. So, this is the procedure through which we can generate the time delay with the help of the resistor pair, single resistor and the nested loop, and this is the program through which we can design the down counter and generate the time delay between these two count value, and finally send the value to the output port. Thank you very much.